And the topic we are going to cover in this video is going to be Gibbs energy and fugacity of a component in a mixture. We have already derived the expression of the fugacity. We have defined fugacity in relation to the Gibbs free energy for a real fluid, for a pure component. Fugacity equality establishes the chemical equilibrium, vapor-liquid equilibrium, in two phases. The fugacities of the components in a pure fluid should be equal. Similarly, fugacity of a component in a mixture should be equal to its counterpart in the other phase also. So fugacity equality of the fugacities is our criterion, one of the defining criterion of equilibrium. Now we have to be able to estimate the fugacities of those components in the mixtures, considering the fact that we have now non-ideal mixtures. But of course we have to identify the non-ideality of the mixture relative to its ideal counterpart. So in this video we are going to establish what is an ideal mixture and how we are going to account for the deviation from that ideality. Now let's first remember the definition of the fugacity. Fugacity, with respect to the Gibbs free energy, is defined in this equation. It is the pressure multiplied by an exponential factor, which is scaled to the thermal energy of the difference between the Gibbs free energy of our component minus the ideal gas Gibbs free energy of the same component. And when we have carried out the algebra of the Gibbs free energy, remember that the Gibbs free energy was, let me write the differential form, minus S dt plus V dP. We have derived the Gibbs free energy for the situations where we maintain the temperature constant. When we maintain the temperature constant, this term is eliminated, so we limited the Gibbs free energy to an integral between the volume and the differential change in the pressure. Substituting this here left us with an equation as such. This is the difference of the Gibbs free energy of our component minus the ideal gas Gibbs free energy of the same component under the same temperature and pressure. Of course, in this expression, volume, ideal gas volume is RT over P, and this is the volume of our fluid, whichever phase it might be in. Definition of the fugacity. Now we are going to develop the counterpart of the same definition of the component in a mixture. So now we have added the definition of a mixture. Mixture means that we have more than one component. When we have more than one component, we have to take the mole fractions of those components into consideration. So in addition to temperature and pressure, we need to take the mole fractions into consideration. Now we are going to, of course, specify the fugacity of whatever the component, and this overbar will indicate that that fugacity belongs to this component in a mixture. All right? We have defined overbars as the identifiers of the partial molar properties. For the fugacity, it is not the partial molar definition. For the fugacity, the overbar indicates that it is the fugacity of that component in a mixture, because we can have fugacity of that component that is not in a mixture as a pure species, right? So fugacity of this component in a mixture under that temperature, that pressure, and that composition is pressure multiplied by the mole fraction of that component in that mixture multiplied by the exponential 1 over RT, the difference between the Gibbs free energy of those components in a mixture subtracted from the corresponding ideal gas mixture. All right, so the general definition is retained. It's the difference between the Gibbs free energy of the component in the mixture minus its counterpart in the ideal gas mixture. All right, and of course this simplifies to a function p times xi multiplied by exponential 1 over RT Vi minus Vi ideal gas, and these overbars bear the correct meaning. So we have partial molar Gibbs free energy in the mixture, partial molar Gibbs free energy in the ideal gas mixture, partial molar of component I in the mixture, partial molar volume of component I in the ideal gas mixture. Now the ideal gas mixtures are additive, so the volume of a component in the ideal gas mixture is going to be the total volume multiplied by the volume fraction or mole fraction in the ideal gas mixture. This is going to be a relatively simple definition. Let's see the Gibbs free energy of component I in an ideal gas mixture. So let's start from, again, this definition of the Gibbs free energy, and we're going to have an ideal gas mixture, and in that ideal gas mixture we're going to have components. Let's have a binary ideal gas mixture of A and B, and let's estimate the mixture properties. The volume change upon mixing is going to be negligible. Negligible is not the correct word. There will be no volume change upon mixing for ideal gas mixtures because ideal gas mixtures are additive. So let's start from the Gibbs free energy of component 1. It will be minus S1 dt plus V1 dP. The Gibbs free energy of component 2 is going to be minus S2 dt plus V2 dP. So we have those pure components, and we are going to mix them at constant pressure. All right? And at constant temperature also. So let us look at how entropy changes for a species, whether it is a pure or it's in a mixture. Remember, we defined the entropy, differential entropy, relative to the internal energy as du over T plus P over T dV, right? And du was Cv dt over T plus P over T dV. For an ideal gas, this was CV star, and P over T was R over V. And let's just start from specific intensive properties to proceed a little bit trouble-free. So here we have two terms, CV star dt over T plus R dV over V. All right. Now, the integration of this is going to give us, each of these terms can be independently integrated, CV star ln T2 over T1 plus R ln V2 over V1. S2 minus S1 under ideal gas conditions. All right, now this is our expression. Let's just keep temperature constant so that this term disappears. So our entropy of ideal gas between state 1 and 2 is only subject to a change in volume. R ln V2 over V1. Right? Our pure substance is going to either expand or contract. Expansion and contraction is going to change the entropy of a fluid. So let's take the derivation from here and proceed to derive the pressure equivalent of this expression. Again, we are dealing with an ideal gas. Delta S, I will go shorthand, is going to be equal to CV star. I'm just transferring the expression here. T2 over T1 plus R ln V2 over V1. Now I'm going to, instead of volume, I'm going to introduce the ideal gas equivalent of volume, which is R T2 over P2. And of course, for this one, R V1, R T1 over P1. When I do so, I have CV plus R ln T2 over T1 plus minus R ln P2 over P1 delta S. This was C sub P, right? So here I have an expression which gives me the entropy change of a fluid if its temperature and pressure changes. Now let's take a chamber filled of gas 1 and a pressure of P1 T. Let's put T outside our chamber. Chamber 1 is filled with gas at P1. And into this chamber, I'm going to blend the second gas. So let's say that PA, all right? Initially, I have only gas A. Its pressure is P sub A. Its temperature is T. And I'm going to blend into this gas the gas B. All right? This container is at constant volume. I'm going to introduce P sub B of B into this chamber. So at the end of this process, I'm going to have N sub A plus N sub B as the total number of moles times R times T is going to be over V is going to be the final pressure. While I can write this, I also can write P sub A to be equal to RT over V times N sub A, and I can write P sub B as RT over V N sub B. Why do I write everything in such fine detail will be clear in a moment. Now, what is the mole fraction of B in this chamber? Mole fraction of B, I will indicate it by Y, just to make sure that I don't mix liquid and vapor mole fractions, because that is going to be one of the key concerns that we will be dealing with in this chapter, in this section. So this is the gas phase mole fraction of component B. It is equal to NB over Na plus Nb. And of course, for the ideal gas mixtures, it's going to be Pb over Pa plus Pb is going to be Pb divided by P total. Right? Now I have a new expression for Pb. Pb is equal to P times Yb. All right? And now I'm going to calculate how does the entropy of pure A after being blended into B has changed. What is the initial situation? Initial situation is that I have pure A at P of A at constant temperature. At constant temperature, I don't have this term, minus R ln. Now let's see what the analysis is going to show us. What is the initial condition? I'm checking the entropy change of species A. What is the initial condition? Initially, it was at P sub A. All right? In the final condition, my pressure has changed. My P2 of component A is YA times P total. All right? So let's leave this one here and let's derive the volume equivalent of the same expression. So now let's take the volume equivalent equation. Entropy change of species A under a constant pressure condition. So I have 1 atmosphere of A. I blend in some B into this 1 atmosphere of A, and I just would like to find out what is the entropy footprint of that mixing process. R ln volume of this component in condition 2 divided by volume of this in component 1. So since I'm going to do this at constant pressure, the total volume occupied is going to be constant. R ln initial volume will be V1. The final volume occupied by component A is going to be YA times V1. All right? So the total these terms, let's summarize this and then come back to the discussion. These terms will cancel, and the entropy change of an ideal gas mixture will be R ln YA. So let us remember this. Because this is going to be our anchoring relationship, that when we mix ideal gases, we don't have any change in total volume, or we don't have a volume change upon mixing, we don't have an energy change upon mixing, because those ideal gases don't interact, they act like billiard balls. But we have an entropy change upon mixing, because we have now unlike substances blending into each other, and this term gives us a measure of the randomness of the mixture, right? If it is fully randomly mixed, then we have an ideal gas mixture, and the entropy change of mixing two pure components into a mixture is going to be represented by the gas constant multiplied by the natural logarithm of the mole fraction of that particular component going from a pure to a mixture. Now, the total entropy change, so this is the entropy change of component A. The total entropy change as a result of this mixing process should be the summation of entropy change of component A multiplied by YA plus component B mole fraction times delta S ideal gas of B. So if you write this, we get the following expression. R YA times ln YA plus YB times ln YB. Okay, or in its most general form, you're going to have a general expression, summation over all species, yi ln yi. right? So this is the entropy change of making an ideal gas mixture starting from its pure components. If this is so, let's look at the Gibbs free energy. Delta G of ideal gas mixture is going to be, at constant temperature, T times delta S ideal gas mixture plus V times delta P. So again, we are comparing, we are looking for the Gibbs free energy change of an ideal gas at constant temperature and pressure. We are just looking for the Gibbs free energy change induced only by making a mixture under constant temperature and pressure conditions. The constant pressure condition is going to eliminate this term. Constant temperature condition is going to keep this term. This is going to be RT summation of YI ln YI. This is the second equation that we are going to use very frequently. All right, so if we mix two ideal gases, the volumes will be additive. There will be no volume change upon mixing. Energies will be additive. There will be no energy change upon mixing. But you're going to have entropy change upon mixing, and energies that have entropy change in their fundamental descriptions are going to change as well. Those two energies are Gibbs free energy and Helmholtz free energy. So upon mixing ideal gases, we are going to have changes in entropy and changes in Gibbs free energy. And similarly, we are going to have changes in Helmholtz free energy. Now we are going to estimate the partial molar entropy of component I in an ideal gas mixture at constant temperature, pressure, and mole fraction xi. The partial molar entropy of the component I in the ideal gas mixture is going to be referenced to its pure component entropy, molar entropy at the temperature T and P minus R ln xi. This term is the entropy change that occurred upon mixing at constant temperature and pressure. The Gibbs free energy definition of the Gibbs free energy being minus S delta T plus V delta P is going to take us from that expression to GI ideal gas mixture of T, P, Xi, partial molar Gibbs free energy of an ideal gas mixture to be equal to molar Gibbs free energy of that component under ideal gas conditions at the same temperature and pressure, plus RT ln xi. The partial molar property, theta I, is something we should remember, was the partial derivative of a property with respect to the change in the number of moles of component I under constant temperature, pressure, and keeping all other components constant except this one. So the partial molar Gibbs free energy of a fluid, of an ideal gas, partial molar of component I in an ideal gas mixture, is the partial derivative of the total Gibbs free energy in the ideal gas mixture. It has to be referenced to the ideal gas, pure component ideal gas Gibbs free energy, plus the Gibbs free energy change due to the entropy change upon mixing. Now, before we proceed any further, let's define the internal energy change, volume, enthalpy of the ideal gas mixtures. So the internal energy of an ideal gas mixture is going to be the summation of internal energies of the components, pure components, enthalpy of an ideal gas mixture is going to be the summation of pure component enthalpies all right, but the entropies of the ideal gas mixtures will be entropy of the pure ideal gas components minus the entropy change upon mixing, and similarly Gibbs free energy of the ideal gas mixtures will be xi of the ideal gas minus RT xi ln xi. This is plus RT. All right, so we have the full set of the definitions of the energies and entropies of ideal gas mixtures. Internal energy of an ideal gas mixture is additive. Enthalpy of an ideal gas mixture is additive, not the entropy, not the Gibbs free energy. And we have, of course, Helmholtz free energy equivalent of this expression, AI, ideal gas, plus RT Yes, xi. All right, so this frame sums up the ideal gas mixture properties relative to their mole fractions. Yes, we are going through all this trouble in order to be able to make estimations in phase equilibrium or chemical equilibrium. So let's start by considering problem of phase equilibrium of more than one components. So we have a mixture of A and B in the liquid phase, and we would like to calculate the composition of A and B, which is in equilibrium with this liquid. And the process is going to be at constant temperature, at constant pressure. Of course, our definitions of equilibria so far has established that we now know that in order to have an equilibrium, we have to have, if this is phase 1 and if this is phase 2, we have to have equality of temperatures, equality of pressures, and equality of the fugacities for the components in both phases. All right? So, temperatures are equal, it's intuitive. Pressures are equal, it's intuitive. Now we're going to use the equality of the fugacities in both of those phases of component A and component B. So let's just be a little bit more specific. Let us write explicitly fugacity of component in phase 1 in a mixture is going to be equal to fugacity of component A in phase 2 in a mixture. All right, here is the vapor phase, here is the liquid phase. Similarly, we're going to have fugacity of component B in phase 1 to be equal to fugacity of component B in phase 2. Now we're going to put facts together. Let us have an ideal liquid mixture. If our mixture, liquid mixture, is ideal, it is going to have no enthalpy change upon mixing, and no volume change upon mixing. Volumes will be additive, and energies will be additive. All right? The only change upon mixing we are going to encounter would be due to the entropies. We are going to start from pure components, and we mix the pure components. This is going to increase the total entropy. Let us have an ideal vapor mixture. For the ideal vapor mixture, the same conditions will prevail. From those starting points and the definitions of the fugacity. Let's see what the fugacity equality is going to take us. Fugacity of our component in the liquid phase is going to be fugacity of component A in the liquid phase is going to be P times Xi. So we have to be careful. What is that pressure that we are talking about? What is that mole fraction that we are talking about? And which volumes are we going to use here? And fugacity of the vapor component I in the vapor phase is going to be, what will be this pressure? What will be this mole fraction? And what will be those volumes? It's going to be the question. Now, if I'm going to have an ideal vapor mixture, there is no volume change upon mixing. There is no energy difference upon mixing. I'm going to make one more assumption, and I will have an ideal vapor mixture of ideal gases. If I have an ideal vapor mixture of ideal gases, my fugacity of component I in phase 2 should be equal to the total pressure times the mole fraction in the vapor phase. Right? So this term is going to be 0 because I have ideal mixture of ideal gases. This is going to be the volume of an ideal gas. This term is going to be 0. This term is going to be 1. My fugacity of component I will be the total pressure times the mole fraction of that component in the vapor phase. Now we have an ideal liquid mixture. Now we have to estimate the fugacity of component I in that ideal liquid mixture. Again, our expression is identical. Fugacity of a liquid phase component was determined through passing through the ideal gas conditions. But if you remember, the fugacity of a pure component in a liquid mixture, where again the volume change, when the volume change upon mixing is negligible, was reduced to the saturation pressure of the pure component. Now we are going to multiply it by its mole fraction. The pressure of the fluid that of the liquid, the pressure of the liquid that is going to be translated to the fugacity of the component in a liquid mixture, ideal liquid mixture, boils down to the saturation pressure. And when we substitute it in here, liquid phase mole fraction. Now we are going to take these two and we are going to say that they are equal. So we have an ideal liquid mixture, an ideal vapor mixture of ideal gases, and we have equated their fugacities. All right? This expression is known as the Raoult's law. All right? So by knowing the pure component vapor pressures, by knowing the liquid volume fractions, by knowing total pressures, we are able to calculate the corresponding mole fractions in the vapor phase. So, one more time. I have a mixture of A and B in the liquid phase. This liquid phase is ideal, no volume change upon mixing, no energy change upon mixing. They evaporate and they form an equilibrium phase in the vapor state. We are looking for the mole fractions as in the vapor phase. At equilibrium, we have equality of the temperatures, we have equality of the pressures, of course, equalities of partial molar Gibbs free energies or chemical potentials, which translates into fugacities. All right? And starting from this, applying the conditions that we deduce because our mixtures are ideal, we arrive at a relatively simple expression which we call the Raoult's law, which says that the mole fraction in the vapor phase can be estimated from the mole fraction in the liquid phase, total pressure, and the vapor pressure of component I in the pure state. So nothing is changing upon mixing except entropy. We have derived an expression that treats the mixture as if two individual mixtures, two individual components are evaporating. The only condition that we see is that the space occupied in the gas phase is going to be reflected by the vapor pressure of the pure component and its mole fraction. So this is the Raoult's law. This is the simplest approximation of the vapor-liquid equilibrium estimations, and we are now going to introduce correction factors to the Raoult's law. The correction factors to the Raoult's law is going to now this pen doesn't squeak. Real fluids. So we are going to add correction factors to the Raoult's law. We're going to add a correction factor here. We're going to add another correction factor here. The correction factor here is going to be what we call the activity coefficient, all right? PIV times XI, all right? This activity coefficient is going to take the volume change upon mixing. We're going to, of course, here add a Fugacity coefficient just to correct the fact that we have taken the Fugacity component, Fugacity coefficient as being equal to unity. Remember, Fugacity coefficient, phi I was equal to Fi. Let's start from here. The Fugacity coefficient was equal to F over P, which was this group of equations, and Fugacity of component I is going to be equal to Fi over P times Xi. All right, and it is equal to exponential 1 over RT 0 to P dP. All right? So now we are correcting the vapor phase through a Fugacity coefficient, and we are correcting the liquid phase through an activity coefficient model. But we can use Fugacity coefficients in both liquid and vapor phases if we have a robust equation of state that allows us estimate both liquid and vapor phase Fugacities. Then we can use Fugacity coefficient for the liquid phase P Xi and this is going to be called phi estimations. And this is going to be called phi gamma estimations. So what we are doing is we are bringing the ideal situation a little bit closer to reality by adding correction factors in the liquid phase, and in the vapor phase. And those correction factors can come from an equation of state, which allows us to calculate the partial molar volumes so that we can estimate the Fugacity coefficients, or we calculate the activity coefficients, and the activity coefficients are a reflection of the fact that when we mix two substances, we have an excess Gibbs free energy, one due to a change in entropy, but if the change in entropy is only limited due to the change in the entropy of the upon mixing, in other words, that the entropy doesn't change beyond the fact that we mixed two dissimilar substances, then we call this solution a regular solution, and the Gibbs free energy change is only going to be due to the change in volume upon mixing. So here I'm making one definition after the other. The first definition that I have made was about the Raoult's law. The second definition was about the real fluid estimation methods. The third definition I have made was about regular solutions. Regular solutions have entropy change upon mixing to be equal to entropy change upon mixing of an ideal gas, right? Of an ideal mixture. So there is no entropy change anything beyond the ideal gas mixture. All right? This is the regular solutions, and as a result, the Gibbs free energy change upon mixing is only due to the change in the volume upon mixing, and that change in the volume upon mixing can be used to estimate the activity coefficient.